Hello, and welcome to this Delsys webinar on combining physiology and biomechanics for sports performance. We're pleased to be able to be joined by two speakers, Dr. Thomas Lapole and Gabriel Idda. They'll be presenting their latest research on the energy costs of downhill running from lab to the real world. And these presentations will look to be able to combine EMG and VO2 to be able to provide a holistic overview of sports performance in these real world settings. So the agenda for today will be relatively straightforward. We'll start with an integration of EMG and VO2, what the separate modalities allow us to be able to understand, and then combining the two, what this then enhances our understanding of performance. We'll then move on with a brief presentation from Thomas Lapole in terms of the introduction of the LIBM lab, their research topics, and how they've been able to use Trigno Link within some of their initial explorations. We'll then move on to the current research for how combining these two modalities with the EMG and VO2 allow them to be able to get a deeper understanding in terms of some of the different sports performance metrics. And then we'll finish off with a brief Q&A session at the end. So to start, really the question is, what is EMG? So EMG is the study of muscle function through the inquiry of the electrical signal that the muscle emanates. So we're really looking at how the brain helps to be able to control movement and how the EMG signal can help us to understand key questions such as what are the basics of motor control, properties that govern muscle contractions, how does fatigue manifest, and how does it affect specific muscles differently, and then what factors influence muscle performance. And a lot of these different insights allow us to be able to understand differences in human performance and allow us insights into certain metrics such as asymmetries and imbalances, how we can look at muscle timing to be able to understand coordination, and then how we can also look at fatigue to be able to see what sort of detrimental effects that will have on performance as well. And by taking into account a lot of these different metrics, we're able to give a lot of information to trainers and researchers to be able to develop more effective training protocols through tailored solutions. And by assessing these asymmetries and balances, we're able to prevent injuries and also be able to understand different types of overuse situations so that we can get the most out of athletes from both the performance and the injury mitigation side. And coming on to VO2 as a separate modality to be able to understand the cardiovascular output. So VO2 is a commonly used tool within sports science, physiology, and human performance assessments. It measures the maximum amount of oxygen an individual can utilize during exercise. VO2 is a measure of aerobic capacity and is often used to be able to assess an individual's fitness level, to establish resting metabolic rates, examine ventilatory thresholds, and provide information on the time spent in different training zones during a protocol. We're proud to be able to partner with VO2 Master, as this really is the first and only true portable VO2 analyzer on the market. VO2 Master provides a new platform to analyze performance, and through the cable-free design allows for metabolic performance to be monitored on the go. And that's where really the wireless nature of their system fits in perfectly with the Trigno system in terms of the wireless communication and the hands-free data collection that we can perform anywhere, whether it's inside the lab or outside the lab. And this then comes to the question of how we can then combine EMG and VO2. And this offers researchers a whole range of different advantages for understanding the interplay between the neuromuscular system and the cardiorespiratory response. For instance, when assessing an athlete's VO2 max or trying to personalize some of the training programs, the VO2 will really allow us to be able to see the overall efficiency of movement and the energetics involved within performance, but the EMG will allow us to have a more localized view of which muscles are contributing towards the level of performance and if there are any specific muscles that need to be targeted to avoid the early onset of fatigue. So being able to combine these different modalities and metrics provides a more holistic and whole-rounded insight into human performance and rehabilitation. And at Delsys, we are known for producing a wide range of high-fidelity EMG sensors, ranging from standard single bipolar electrodes all the way up to multi-channel and high-density EMG solutions. However, we are also experts in wireless communication, and this has allowed us to be able to expand on our product portfolio with the addition of other third-party physiological metrics through the addition of the Trigno Link device. So with the Trigno Link module, you can now bring in external data via Bluetooth and ANT+ from other commercially available products. This includes, but not limited to, the heart rate data, VO2, muscle oxygen saturation levels, grip strength, and many more. So this all then combines a lot of these different sensor modalities into a single software platform, Trigno Discover, alongside our EMG from the Delsys EMG Trigno systems. And this is then when we start to be able to get a more complete and holistic overview of human performance and movement as we bridge the gap between biomechanics and physiology, where we can still get a lot of that rich EMG data from the neural and motor control side, but then we can also bring in the oxygen uptake data from how the oxygen is delivered through the cardiopulmonary systems, the cardiovascular effort through the heart, and the oxygen delivery through the blood to the muscles, then how the muscle also then draws and extracts the oxygen from the blood to be able to use it for energy production at the level of the muscle, and then tying all that in together to be able to understand the mechanical output and how movement is generated and regulated through different demands and sports performance. And we can see that all of this data is then very succinctly and easily visualized within our Trigno Discover software. So you get the rich data coming from the EMG in terms of the activation timings, the amplitudes, and all of the other metrics that we can draw from the EMG data. But alongside that, then we get the easy visualizations of the physiological data from VO2, from oxygen saturation of the muscle, alongside heart rate and other mechanical stimuli as well. So I'm pleased to be able to introduce our first speaker, and this is Dr. Thomas Lapole from the University of Jean Monnet University in Saint-Etienne. So Thomas was named Vice Dean of the LIBM lab in 2020, where he conducts his research today. His research projects focus on the plasticity of the neuromuscular function in response to exercise and rehabilitation strategies. His goal is to improve decision-making knowledge and non-pharmacological rehabilitation protocols through the assessment of therapy modalities, with a strong focus on the field of vibration therapy. So unfortunately, Thomas cannot join us today, as he is enjoying some of the best that sports can offer at the Olympics in Paris, but he has sent the following video introducing some of the research that is done across LIBM and their explorations with the Trigno Link device.
Good morning or good afternoon, and thank you, Jonathan, for the introduction. I'm sorry first for not being able to present today in live because I actually attend the Olympic Games in Paris. But through this video, I would like to introduce you this seminar on some work we performed within our lab with Gabriel, Guillaume, and Leo. We would first like to introduce you our lab, the LIBM, which is located in France on 3 universities, Lyon, Chambéry, and Saint-Etienne, and I am actually the lab director for Saint-Etienne. Within our lab, our main research focus is to study the biological aspects of motricity with both industrial and clinical developments aiming at improving health and performance. As examples, we try to understand and model the effects of physical exercise. We want to study and prevent pathologies induced by physical exercise, and we also aim at investigating the potential positive effects of physical activity on health and quality of life. To have a better idea of what we can do within our lab, here is a short video showing some equipments we have in Saint-Etienne within our physio lab. So for doing some force, power, velocity profiles, also for doing neuromuscular function evaluation using both electromyography and electrical and magnetic stimulation techniques. We have different kind of dynamometers for isometric, isokinetic measurements, but also for fatigue measurements. We can also do some muscle measurements using echography. And we have also possibilities for more physiological measurements, including spirometry, oxygen uptake, both within the lab, but also, as you will see, on the field. So we also have a motion analysis laboratory, including force plates, instrumented treadmills, motion capture analysis, and all those measurements being possibly coupled with EMG. And to conduct those research activities, we supervise a lot of PhD and also master degree students doing their internship. We have several master degree programs in both French but also in English for international students. And all those programs are now together within our new graduate school on physical activity, training and health in sports sciences. So the PATH graduate school. Do not hesitate if you are a student willing to come and benefit from our research topics and facilities. And also do not hesitate if you have some students that may be interested in it. In the context of our master degree program, I had the opportunity to work with Delsys on a small project aiming at discovering the Trigno Link device. And this was something we performed with two master degree students during their first year internship within the lab, Hugo and Ryan. And we performed a study on the correlation between ventilatory thresholds and EMG fatigue thresholds during cycling exercise. For instance, we know that during incremental exercise, there is an increase in both ventilation and VO2, and that this relationship can help to distinguish two different ventilatory thresholds, where ventilation will increase more than oxygen consumption. And similarly, it has been suggested that the use of electromyography can help detecting an EMG fatigue threshold that may correspond to the secondary voluntary threshold. So while several studies demonstrated the correlation between secondary voluntary threshold and the EMG fatigue threshold, we wanted to replicate those results using the Trigno Link device with a full synchronization between VO2 measurements and EMG measurements. So this is something Hugo and Ryan performed on 8 years during an incremental cycling protocol with both ventilatory flow and EMG measurements using the VO2 Master and the Trigno Link device. And we had some visual inspection of both ventilatory and EMG thresholds. The result, we were able to plot ventilation against VO2 as well as EMG of the vastus lateralis muscle against VO2. So to detect ventilatory threshold and EMG fatigue threshold. And we had a quite nice correlation between those two thresholds, suggesting, as already demonstrated within the literature, that the EMG fatigue threshold can be a good index of ventilatory threshold. So after discovering the Trigno Link device, we wanted to go further by designing together with Delsys an original study. And this is what we performed in the context of the master degree of the second year internship of Gabriel Idda that I supervised with Guillaume Millet. And we performed a study on the ideal slope in downhill running. And I'm glad to introduce you Gabriel, who will present you the results of his internship.
So thank you very much, Thomas, for your introduction to the research. And now we would like to be able to introduce our second speaker, Gabriel Idda. So Gabriel is Thomas' student, and after graduating high school in 2018, Gabriel began his bachelor's degree in sports science at Jean Monnet University at Saint-Etienne. He's currently pursuing a master's degree in the training and optimization of sports performance, where he's working full-time on his project, What is the Ideal Slope in Downhill Running? a laboratory and field study to get insights into biomechanical and physiological determinants of the cost of running. So this will be the research that Gabriel will present on today, and I hand it over to him to be able to take it on from here.
Perfect. Thank you, Jonathan, and good morning, everyone. Thank you, Jonathan, for the introduction and the opportunity to be able to share my master thesis project. So I'm just going to share my screen. Okay, so as I said, we're going to talk about running and specifically the downhill running. What is the ideal slope in downhill running, biomechanical and physiological determinants of cost of running. So this was my project during my master thesis, and I'm going to share with you today the introduction, methods, results, and everything that's going with that. So first about running, as you may know, there's many different factors for performance in running, and the one we are looking at today is the cost of running. So the cost of running is the energy you need to that your body consume while running, and there was a lot of study on cost of running in level running, some on uphill running, but there's really few studies on downhill running. However, we know that downhill running has a specific technical abilities, the importance of eccentric work, the importance of the elastic energy storage, etc., etc. And also, there's a really boom in the participants of trail and ultra trail. For example, we have here the UTMB, Ultra Tour du Mont Blanc, that has a lot of participants and it's just growing years and years. So we may ask, does the things that applied on level and uphill running apply as well on downhill running? So there should be some differences. So for this background on literature on this, we have first a study of Minetti et al. That studied downhill running in 2002, and they showed that there was an optimum slope between -10 to -20 degrees, where you consume less oxygen, where you consume less energy. So you're more efficient between -10 to -20 degrees downhill running. And then later, Lemire et al. Showed again the same results, where they showed the optimum slope again between -10 to -20%, depending on the speed as well of the running speed downhill. So we know that there's an optimum slope between -10 to -20 degrees, where we consume less energy. What else do we know? We know that for muscle activity, the Vernier et al. Show that for the vastus lateralis activity in downhill running, there's a trend that the vastus lateralis goes up. For example, here at -10 degrees, -10% degrees. So this is probably due to the braking forces. So the vastus lateralis and the quadriceps muscle might be involved in the braking forces, so that's why it's going up. And for the gastrocnemius lateralis activity, so the calf muscles, we can see that there's a trend of the decrease of the EMG activity, but there's nothing significant. So there's still a lot of things that we don't know, a lot of biomechanical and physiological factors that remain elusive in downhill running, specifically in field condition. So we have different objectives in this master project. First, it was to study in the lab the EMG, the evolution of the EMG and the VO2 at the same time in a synchronization way that was possible thanks to the Trigno Link device, and then move it outside the lab. So to do this, we have a protocol. First, we did some isocinetic tests that I'm not going to share today, and we did a familiarization with downhill running at 5 different slope: 0, -5, -10, -15, and -20% degrees at 2 velocity, 10 and 12 kilometers per hour. And then they did the protocol. So they ran 4 minutes, like there was 10 boats, 5 conditions for 5 slope and 2 conditions for 2 speeds. We had 14 participants, and here the age around 26 years old. They were all from the sports science department in Saint-Etienne, and there were 11 males and 3 females. So we had first measured the VO2. So the VO2 was measured with the VO2 Master that Jonathan presented earlier today. and that allowed us to measure the oxygen cost of running. And then we measure the electromyography activity with the Delsys device, as you can see here on the video. So there was EMG activity on the vastus lateralis and on the gastrocnemius lateralis. So the data for the VO2 and the EMG were taken on the last minute of every bout of running. And then thanks to the treadmill, we also had the ground reaction forces, so braking forces, propulsive forces, impact peak, etc., etc., and as well as spatiotemporal parameters. So here you have two videos of the protocol in the lab. So you can see on the left a participant running with the VO2 Masters and the EMG activity. And on the right, you can see the synchronization of the data on the laptop for the EMG and the VO2. And on the big screen, you can see the force plate data. So first, we're going to talk about the optimum slope. So we can see here at 10 kilometers per hour, we could find this optimum slope again. That was between minus 10 to that was around minus 13.7%, and at 12 kilometers per hour, that was between around minus 14.3%. So these results are consistent with the previous study where they shown the minus 10 to the minus 20% optimum slope. So we could find the same results in the lab. And know what's it's important is to look at the EMG, because that's what it's important. And we try to look and calculate the optimum slope with the EMG activity of the gastrocnemius lateralis activity. As you can see here, we found an optimum slope at minus 16.3% for both speed, but still the results are a lot of, there's a lot of difference between participants. There is a lot of intervariability, probably due to the technical ability of running downhill, because participants can have more rear foot or front foot running, and that could change the EMG activity. And then we can look as well at the vastus lateralis activity. As we can see, the vastus lateralis activity, there's a trend that the vastus lateralis activity is going up while running downhill. So on steeper slope, you have a higher activity of vastus lateralis, so you need more vastus lateralis and quadriceps muscle activity in downhill running, and we can see later that is going to be correlated with the braking forces. So we have the running economy and the EMG activity. So we did different correlation. We did measure correlation between first on the left running economy. So running economy is the cost of running, is the oxygen cost of running that we measured with the VO2 Master, and we tried to do a disrupted measure correlation with the gastrocnemius lateralis activity. So we could see that there's a strong correlation between these two. So while the running economy is the lowest, the gastrocnemius lateralis activity is the lowest at the same time. So it means that you have a lower activity while running downhill of of calf muscles. But here, as you can see, there's no correlation, for example, with the vastus lateralis activity. So possibly the fact that we consume less energy in downhill running could come from a lower activity of gastrocnemius lateralis activity and the lower activity of calf muscle. Still, we didn't measure the other muscles, so there could be an impact as well of glutes muscle, hamstring muscle, etc. But first, there's a strong correlation between gastrocnemius and running economy that could be important to develop in downhill running. And now we can look at the braking and propulsive impulse in downhill running. So first on the left, we have the braking impulses. As we can see, it's a really linear regression, very between measure correlation between slope and braking impulse. As you can see, there's an increase of the braking impulse that is logic in downhill running. So the more you run at steeper slope, the more you need to brake. So you need to brake to slow yourself. And it means that on steeper slopes, you need to slow yourself and just brake more. And on the opposite side, you have a linear regression between slope and propulsive impulse. So on steeper slope, you need less propulsive impulses. Now, what could be interesting to do with this result is to look at the EMG activity and the correlation between these two. So first, we look at the vastus lateralis EMG activity and the braking impulse. So as we can see here, there's a correlation between the vastus lateralis activity and the braking impulse. So vastus lateralis activity was correlated to braking impulse. So this means that the vastus lateralis is mainly implied in braking. So while you run down in downhill, while doing downhill running, you need your quadriceps to brake, and that's explain why there's a higher activity of vastus lateralis. And on the right, you can see that for the gastrocnemius lateralis and calf muscles are really well correlated with the propulsive impulse. So there's a less calf muscle activity, probably due to less propulsive demands in downhill running, and that could induce as well lower running economy in downhill running on steeper slopes. So now, what could be interesting, and what is the second objective, is to try to move this result that were inside the lab to move it outside the lab. So we did kind of the same protocol. We had a third session where the participants run outside for 50 to 100, 200 meters, and where we could measure the EMG and the vastus lateralis and the gastrocnemius lateralis at the same time again, but this time outside, and we'll try to see if these results are consistent with the ones we had inside the lab. So here we have two videos. So of the downhill running project, we monitored the speed with the bike that was monitoring the speed, and then the participants was running behind the bike with the EMG on the calf and on the quadriceps. So here the first result, we are going to look first at the gastrocnemius lateralis activity. So for the GL activity, we could see here that there was differences. So a color represents a participant, and the circle represents indoor result, and the triangle represents outdoor result. So here it's just a result for 3 participants that I want to share. So we can see that there's even if it's still following the same trend, we can see that there's differences between the results inside and outside the lab. And this could be explained because outside you don't have the same need of probably propulse, and you don't have the same fear. For example, while you run on treadmill, I don't know if you ever try to run on a treadmill at a steep slope, for example, minus 15%, but there's this fear of falling. So this fear outside is less here, and you're more used to run outside on steeper slopes than inside on a treadmill. So this could be a reason for these differences. And if we look at the vastus lateralis activity, we can see again that there are some differences. Even if the differences are not that big, we can see that there's some differences. So in conclusion, we could see that there was a correlation between running economy and the gastrocnemius lateralis activity. Still, this correlation is not perfect, and there's potentially an importance of the other muscle, as I said, the calf, the glutes, and the hamstring, and it's the combination of a whole thing that could explain the running economy. And then we saw that the braking forces were correlated to the vastus lateralis activity that are mainly due to eccentric forces and that are going up in downhill running, while the propulsive forces and gastrocnemius lateralis activity are as well correlated. So the gastrocnemius, the calf muscle are mainly in a concentric way of working and are going down in downhill running. And then lastly, we could see that the result from outside and inside differs. So even if they follow, the results inside the lab could show us a trend firstly, but there's a need to measure the things outside. And this is doable thanks to the Trigno Link device. So we could measure outside the EMG and VO2, and there's a real need to move the data from inside to move it to move from the lab to the field, and have, for example, the EMG plus VO2 data in the real life and during real conditions, for example, during trail running, etc., etc. Here, on our condition, it wasn't possible to measure VO2 due to just a small distance. 200 meters is not enough to measure VO2, but for example, if you have an athlete running doing trail running, doing long distance running, you can measure VO2 at the same time with EMG, and that could bring you some real important results. And thank you for your attention, everyone, and thank you for listening. And thank you, Delsys, for giving me this opportunity to share my thesis project, master thesis project.
Thank you very much, Gabriel. Just pop my screen back on again. So at that time now, do we have any other questions that came in for Gabriel or for the combination of EMG and VO2 in relation to some of the work they did, any work that you're thinking about doing yourself, or some of the future explorations for combining these two separate modalities? Okay. So, I can start off with one for you, Gabriel. In terms of any next steps within your research, are you looking to be able to combine the VO2 measurements with any more different muscles to be able to understand the interplay between multiple muscles and then the running economy?
Good thing is going to be measure more muscles. For example, as I said, on my research, we were just able, it was just a master thesis research, a project of 6 months. We could just measure gastrocnemius activity and quadriceps activity, but as I said, hamstrings and glutes could have a real impact as well. And also, one thing that could be important is to have accelerometers on the foot, for example, to just look at the running pattern. That could also impact this running economy, and look at different running patterns that could explain the difference in EMG activity between the participants and this high inter-participant variability. So yeah, in the next steps, it could be good things to measure VO2, EMG, and more muscles, and at the same time with accelerometers. So we could have better insights on the impact of and the combination of the body to explain this running economy.
So we have another question that came in. So from Mandeepa. So great talk, Gabriel. Comparing outdoor and indoor, were you able to understand the changes in VO2 data? And I think you touched on some of those limitations, but would you just be able to expand a little bit as to what could be done in the future?
So we couldn't look at the VO2 data outside, so because we just had here in Saint-Etienne, we didn't have long enough steep slopes to measure the VO2, so it was just 50 to 200 meters. So on 50 or 200 meters, you can't have a stable state of VO2 to measure the VO2 outside. So we couldn't compare this result from the inside. We could just compare with the EMG results. But this could be a way, this is a thing to do in the next step, is to find long enough slopes and road with a constant slope. So we could measure and look at the difference between the VO2 and the inside and outside the lab. And there's probably going to be one, because if there's differences between EMG outside and inside the lab, there's no reason why there's not going to be differences in VO2 as well.
Good. So we had another question that just came in asking, so foot landing in relation to the center of gravity of the body increases with the braking force. So as slope increases, the distance may vary and increase the braking force. Similarly, the placement of the foot laterally in relation to center of gravity of the body. So do you have any information on this in relation to your work using the instrumented treadmill? Or any of the sort of more lab-based measurements? So I think sort of taking some of those questions, I think that might be a little bit outside of the scope of what the initial research looked to be able to understand, Gabriel. That's correct, looking at the center of gravity and then the displacement of that in relation to the slope of the downhill running.
But center of gravity, we didn't look at it as well. We could have this information, I think, with the treadmill, but I don't really looked at it. Like I'm just going to be I didn't have like enough time during this master project to look at all the data because we had a lot of data in a lot of things to look at: EMG, for ground reaction forces, spatiotemporal parameters, and everything, and as well isocinetic measurements. But the center of gravity could, yeah, as you said, the distance and the displacement may influence the braking forces, and there could have differences also on the left and the right and the move depending on the strong leg of the runners, and that's it. Yeah.
Thank you. Yeah, we can try and provide some more information in an email afterwards as well, as a bit of a follow-up to some of these questions. A question here as well. So how do you see this research translating into more dynamic movements? For example, turns, hops, or landings?
So, for example, turns, hops, and landings, you can just have the EMG activity with this equipment moving outside. So you can test your athletes during their training, during their testing. If you want to have some tests, for example, athletes, I know in football, you have a lot of athletes doing a change of direction, or in basketball, a lot of jump, etc. So you can look at the EMG activity. You can look at the accelerometers at the same time as well with the EMG device from Delsys. And if you want to move it to your training and testing session with your athletes, for example, it's doable, and it could give you a really good insight, I think, and it could be really important for you to test them during their training and during their testing in the real life. And it's important to test athletes inside the lab. It can give you really good results and insight that you need to adapt the training and adapt the charge of the training, etc. But as well, if you can move from inside to outside the lab and combine both, you can have more insights and more precision and be more precise on what you need to work on. For example, specific muscle for change of direction, etc., etc.
And I think to expand on Gabriel's answer there a little bit as well, in terms of how we can incorporate a lot of the VO2 measurements by doing some more of these sort of repeated bout exercises, such as turns, hops, landings, over and over during different training protocols. We'd be able to see how the efficiency of the body would maybe decline over time, and at what point we're able to see some of that fatigue start to be able to start to have a detrimental effect on some of the performance. And by then isolating some of the different muscles, we might be able to see which muscles are sort of instigating some of that decrease in efficiency of the overall performance mechanisms. So if we wanted to be able to increase performance, we might be able to put in place a specific training protocol to be able to reduce the fatigability of certain muscles, and then increase the overall performance output from the VO2 measurements as well. We have quite a lot of other questions coming in, so we might not have time to be able to answer all of them, but we should be able to get answers via sort of emails after the webinar finishes as well. So have you got any, maybe a couple more for you, Gabriel. So in terms of the potential implications for competitive runners versus recreational runners, you mentioned that some of the different EMG strategies that we saw could be down to the experience level of the runners. So how would race strategy or training be able to adjust or be able to be adjusted, focusing on trail or ultra running in recreational versus competitive runners?
So as we saw, for example, in this project, we saw that the vastus lateralis and the quadriceps are mainly implied in the eccentric work. So maybe try to focus on the training for athletes, and trail athletes, to be more focused on the eccentric training for the vastus lateralis. And we could see also in downhill running that the gastrocnemius lateralis activity and the calf muscle who are less active, specifically in downhill running. So there's probably less importance for them in downhill running. And for recreational versus athletes runners, so there's I think there's a differences between recreational and athletes and trail runners, because trail runners are used to run downhill, so they have adaptation. They have a better technical ability in downhill running. So results also could differ from athletes. So in my project, we didn't measure this data on athletes. So we don't really know if the results are going to be the same. Maybe not, because they are don't have the same technical ability in downhill running. And as well, we conducted some research in the lab on downhill running, and we saw that, for example, after a long time running in downhill running, you have a trend to change your running pattern. So because it's going to be more efficient for you, and it's really demanding on your muscle, for example, on your quadriceps. All this eccentric work for long downhill running races is really demanding, and can create a lot of muscle damage. And there's a real need to prevent this, because it's mainly what could impact the performance. If there's too much damage and your athlete is not able to manage it after that, when it's going to be when he's going to run again on flat, on the uphill, it's going to have less power, etc., etc.
Yeah, very good. I think one final question, which might lead on quite nicely from the previous one, and are you able to see or understand any differences in what effect the uneven surface of trail running might have on the EMG results? So for instance, if you consider the flat treadmill running, where it's quite a predictable surface, versus a rocky, muddy or unstable trail that you're running downhill, how that might affect the EMG results.
So this is the next step as well that we wanted to do, that we think about it. So we think about moving from roads to trail running in downhill running as well. So because there the EMG could really differ, because while you're going to have rocks, there's going to be maybe an impact of the tibialis as well, EMG activity, and the impact also to have a higher stabilization of your center of gravity. And because you need to adapt, like the ground is going to be less stable while you're going to put your foot on, and you really need to adapt work around the ankle and around the muscles. So there's going to be probably some pre-EMG activity before the foot entering contact of the ground. So just to make sure that your body is going to be able to stabilize while if it's muddy, if there's work, if the ground's going not to move, but like if there's a work moving on the ground, etc., etc. So probably higher EMG activity on the muscle, just to prevent and to put the body ready to this stabilization that is going to need. And that's my opinion, but that's a thing that we think about it, to move it and to study the differences between the road and the walk running.
Right, yeah. Thank you very much, Gabriel. I think that probably just about wraps up the Q&A session. Any questions that we didn't get around to, we'll try and provide some of the answers via email as a follow-up to the webinar. We'll also be making the recording available. So if you missed any parts, or we can provide the additional recap to the session, we'll be making this available directly via email and onto our social media channels as well. So if you would like to be able to connect with us, to be able to see further updates in terms of some of the research, some of the webinars that we'll have, and also some general news, please make sure to follow us across our social media, with X, LinkedIn, YouTube, and Facebook at Delsys Inc. And please feel free to contact us if you do have any more direct questions at contact@delsys.com. Thank you all for attending once again, and we hope to be able to see you at future upcoming webinars as well. Thank you very much.
Thank you, everyone.